everyone. Thank you so much for joining this session. My name is Mohammad. I'm a ultrasonic application development engineer with Acuren application development team. And I'm very excited to share this topic with you today, which is an explainable machine learning approach to automated analysis of phased array weld inspection. So before I jump into the content here, for those of you who are not aware of our group in Acuren is a small group application development group, which our mission is to basically develop new application, leveraging new technology and custom solution for Acuren so that it enables them to do the most advanced inspection service for their client. And typically when there is a challenging inspection that a client requests that it's not a standard or we haven't done before, that's where we like to receive a call, work on it, and from development bring all the training procedure to train technicians to at the end make sure that it can be implemented practically in the field. But aside from that, we also do some external consultancy work. We do custom application development R&D on targeted projects for our external clients, which some of them you can see on this slide. And our area of expertise is specifically ultrasonic imaging, including all the advanced imaging systems. And again, the focus always is to make sure that they can be practically implemented in the field by training and procedure by technicians. So for today, I just want to talk about this automation of phased array data for welds. But the first question I want to raise is that why do we even need to automate this? Like, why? What's the point? And the simple answer is that in Acuren, actually, we are starting to face new demands, that there are many companies that are actually switching now from manual conventional UT techniques or inspections to these automated phased array inspections. And that creates a little bit of challenge because there is a big shortage of qualified technicians who be certified and can basically answer this demand. So we simply do not have enough technicians for all these new demands. So that's why automation can help. Specifically also that in some cases we have big inspection campaigns. There's a lot of data that needs to be analyzed, and it can be time consuming and can be prone to error. So these are all motivations to do at least semi-automated or automated analysis. And you might think that, okay, in the age of AI, we can use AI to train algorithms to do that. And that's not necessarily applicable here because these complicated AI models like convolutional neural network, they're also great, but they need a lot of data to train, a lot of labeled data. So, and that's why it's not applicable because we simply do not have enough good labeled data that we can give to these algorithms to train them. So that's why we start to think about a new approach that might be much, much simpler to do this automation and be more easy to think about and more easy to explain. And that would be a two-step approach here. In the first step, we are going to implement all the code-specified rules, like how to detect, how to size, how to categorize, by just use the data itself algorithmically. And what I mean by that is that there is no model, there is no AI, it's only the raw data that we load from the equipment in. And we basically go and with these rules that are specified by the code, find indications. When we find them, we size them and make a list of indications. But that list can have both relevant and irrelevant indication in it. And that can be a little bit challenging. Then in the next step, now that we have this list that we got from the data by implementing those rules, we need to parse this list to actually make sure only relevant indications stay there. And I'm going to show you an example. And here is where we want to use a machine learning approach. And I want you to notice that I'm not using the word AI here, although machine learning is a subset of AI, but the focus is a much, much, much simpler models to use because its main job is to actually learn pattern through the data. So training them is much easier and there's less intelligence in terms of like compared to those big neural network models. And it's very important that you realize that where we use this machine learning is not to do any critical tasks in terms of detection or sizing, which can be sensitive. And all it's doing is to parsing the data. And here, this presentation is about to show you how this approach is developed and is now being considered to be used on a big inspection campaign. So one of our major clients, Siemens Gamesa, that's one of our older clients, asked us to help by designing a phase array inspection program for inspecting wind tower welds. These welds, the phase array inspection that we designed, needed to follow pretty strictly the European ISO code. And the welds that we had in this tower had a big range of thickness from 0.5 inch to 1.5 inch. They were all double V, but they had varying different angles in different sections. And we designed an inspection technique in beam tool with a large aperture probe, and we tried to take advantage of compound scans and come up with a big, basically range of angles that can cover these bevels with plus and minus 6 degrees as specified in the code. And the advantage of using compound scan with large aperture probe was that we could cover a bigger range of thicknesses and angle changes in essentially one setup, but obviously with different scan offsets. So we developed this technique. We put the procedure together. Procedure got reviewed by level 3s and approved, and we trained the technicians to implement this, and we start the data acquisition. Then after that, we come now to analysis. So the very first task, obviously, is to do detection. And detection per ISO here was amplitude-based. So it was saying that if you find any indication that is above a certain threshold, that needs to be investigated. That's either relevant or non-relevant. So here is an example. So here you see an indication that is very hot, high amplitude. And you look, you see, seems like it's right on my bevel, and on my merged C scan and B scan, it's kind of isolated along this angle. So this is what I may expect a lack of fusion look like in this. So I consider this relevant. So now I need to do other things like sizing and stuff. But there's this other indication here that is also high amplitude, but now if this beam exit point on this side of the weld is on opposite side, it's close to where the cap is. It's not isolated in the B scan, so either I have flaw everywhere in my scan, or this is really geometry, seems like. So I may consider this to be not relevant. So this is my first step. Now for these ones that are relevant, now I need to size. Again, the rules are very strict and clear. Say when you want to do height sizing of this, you need to go find the max location, go 6 dB drop up, 6 dB drop down, and then that would be your height. For the length, you need to find the extent of your flaw, which is above a threshold, so that would be your length. On top of that, now that you have the indications, depending on the length of each indication and how far they are from each other, you need to consider also grouping these indications and then putting your list. So, and after that, now that you have an indication that the size, you still in your report, you need to decide, is it acceptable or is it rejectable? So again, you have strict rules. You make that decision as 2 by 2 parameters. One would be ratio of the amplitude with respect to the reference, and the other one would be the length of that indication with respect to thickness. And when you put your indication on this, based on those 2 criteria, depending on these regions, you can decide that that indication is reportable, should it stay on the report or not, and if yes, is it acceptable or rejected. And finally, when you do all these, you populate a report that put these indications on, where they start, what was their length, what was their depth, was it acceptable, rejectable, and that's your final report. Now, obviously we train technicians to do this, we write this procedure, they sound simple, but there were challenges. And as you go through and see, these are very long welds, they're 6 meters long, and doing some of these inspection tasks is a little bit tedious and hard, as much as you might not realize if you do it manually. So essentially, when we audit some of these, we see that there are cases that basically technicians are missing indications. There are cases that there are inconsistency in this. And it was very, very important, obviously, for Siemens that everything be done perfectly. So we actually contracted to do more audits, more training, and make it better, better, and better. But at the end of the day, we realized that this is a tedious task. Finding small indications that their amplitude can be close to thickness. When you have a 6 meter long scan, it's hard. And when you find them, there are many geo indications that you need to basically call non-relevant. And applying all these rules manually, it's prone to error. And also it takes a lot of time. And we did a study and realized that it takes like average 45 minutes per weld to do this whole process. And if you have like 40 scans in one tower, that's like 60 hours just for one tower. And sometimes you need to do like hundreds of these towers inspections essentially in campaign. So this was the motivation here, that we develop a custom software that its job is specifically to dedicate to make this task easier. And we call that software assisted analysis with Acuren software team, who is also behind the development of the BEAM tool. And the idea was that make this task easier. So we specified some roles for the software. Say, what software gonna do? It's gonna load the scan file. It can be from X3, X4, any other instrument. And then after it's gonna put the overlay on, and when we give it a threshold, it's gonna detect and size and categorize all those indications algorithmically. Like there shouldn't be any reason that the technician go manually find the stuff. The data is there, you find the points that is above threshold. When you find it, you go and find the bound of 6 dB and you put it on the list. As simple as it is. And the only thing is that creates a fun list of indications, but what is not in there is the intelligence to really separate what is relevant, what is not relevant. All the indications in the region gonna go be founded and sized. So then that's all the assistance that the software is providing. Now the role of analyst is to actually go through that list, not doing any detection, not doing any sizing, but just simply deciding that is that indication relevant or not. So here is a quick demo of how that works. So here we loaded the data, two-side inspection, and this is a merged sectorial view of all 6 meter scan in one view, which is a max stack on both of SKUs, 90 and 270. We designed this technique so we can go to a specific BEAM tool file that was used for that, and now the weld overlays on top, so now it's easier to make sense of what's going on. And as part of that, the thickness of that part automatically is loaded. And what we found, it's easier to make those decisions later, I will show you, is to actually have that thickness fold the data. So we basically correct it to the actual thickness to be easier, essentially, to look at. And then another thing is that by our code, we need to only investigate indications that are within the weld and has region. And so what we can do easily, if we have this overlay, we can go and exclude any data that outside of a has, because it's not part of our job to look into those, and we don't want to get confused. And here now, on both SKUs, we have one view merge of all 6 meters to give us a general idea what's going on. See some indications that you might see relevant, there might be some that might be geo, and on the opposite side also. So that was a data preparation. After this, we go to now try to find indications and presenting this data. We'll find that, and this all can be customizable for different applications. For this application, realize it's easy to present data as like a sectorial view, merge C scan and B scan. Like any other software, the cursor is active. You can move around and go into different frames, and also the angle cursor is also active. So as you move, you see update your B scan. But now this is a point that you want to tell the software what code to follow. It can be ISO, it can be AWS. You need to define those rules. In this ISO one, we say the threshold that we want you to look at is 16 based on our calibration. So find any indication above that. When you found them, do 6 dB drop technique to height size, and use fixed amplitude technique to beat the threshold of 16 to length size them. And we say, okay, find indication. So now there is no model involved, there is no AI involved. It's just go there and find indication. But the problem is now we have 147 indications, which is either this weld is like really fall apart, or like you can't have 147 indications. The reason is the software did what we asked. It said find anything there. It didn't know it's relevant or not. So there's a giant list of indications there for each group. And but the one thing you notice is that for any of indication, all those key information like scan start, length, height, index, max amplitude, etc. is already there. But so we didn't spend any time to do that, but we have this huge list. So we need to do something about it, because this might be actually even more tedious. So here, if we don't do anything about this, the indication list that we will have huge, and obviously it's not going to go on a report. But some of these are relevant. So for instance, if I click on this indication, it shows, software show me where it is in the scan, and I say, okay, this is relevant, it's isolated, it's here. So I want this indication to stay on my list because it's relevant. But for instance, this other indication, I click here, probably this is geo, and you can relate to your training and your procedure to say, seems like it's an opposite skew, I skip to a nominal cap, it's not isolated, I have all many other indications. So you know what, this should be removed from my list. There is another example of that. Essentially now we can look at another one. Another example that again, I may basically look through this and decide that, you know what, this is probably geometry, again, opposite side, top cap, and those are reasons. And you need to notice that all I'm doing is making that decision. And the reason is I don't want to end up with this huge list. So by making this decision, rather than doing any sizing and any of those tasks, this speed up things and makes job easier for me. So I need to go and one by one I can remove this. Okay, I think it's not relevant, I delete, I next one delete, but that also can take time. So we build up some tools that you can basically click and it show you where all those indications are detected. And by this knowledge, now you may think, seems like all of these at the bottom here or at the top here, these are should be geo. So I can just select them all at once and basically delete them. And I can do same here and then grab all of them in one box because I know they are on the opposite side, they are probably geo, and remove them. And now most of those indications that are irrelevant are gone, and I have just few indications in my list, and now I can go one by one and again do double check. So as I do this, again, I keep asking myself only, is it relevant or not? And it seems like I'm just making that decision based on location of this, what skip it is. It can be any training you receive, so it's flexible. Like it reflects how you want to look at this data and what rules you use. But the final point is that now that giant list gonna go down to few lists, and I'm not spending any time to do any of these sizing tasks. And of course, it's not the only side. I have other skew also, and again the same thing with the same logic. I look through this and fine. And if you have one specific campaign, when we do few of these, you basically get the trend of where your geos are, so these tasks also get easier and faster. But now it's much easier to just look through these one by one because that there are not so many. And I specifically try to choose a file that in fact has more flaw than usual to get the point that even when this task seems to be tedious, it's gonna be fast. And now my end table is not that giant list, it's just a few indications that are relevant, they're all sized, and here I can click report, and my report is being populated, all that table is here with that information, and all the screenshots of defect are there. So now, what is the advantage here? So before we even get to automation part, because this was not automated so far, we were involved in making decision. First of all, we are not missing any indication anymore because it's not a technician moving cursors, try to find indication thing. Everything is done by the data. So no misindication. All the rules are being implemented correctly because again, nobody manually move cursors up and down, try to think, it's just the data is there, it's size. So that's by itself was a huge advantage in terms of quality of the analysis, that it reduces the requirement for audits and everything. And on top of that, this process, because you're not doing any of the sizing, it's going to be done much faster. And then we realize it would take like 10 minutes per weld. So now it takes only 14 hours to do a full tower, which is 76% saving in time to just do this analysis essentially. But again, it's not automated yet because our job as analysts, only job, which was actually a very important one, was to convert this giant list into this. And this is where, if you want to do full automation, this is where we want our machine learning approach to come. So machine learning or any model not going to touch those critical tasks. But what it's going to do is to go and try to parse this data and to get it finalized. So what it needs to do is it needs to learn how I did it. So it needs to learn, when I was actually doing it, what was behind my mind, what was in my eyes, what I was doing, and trying to learn with what logic I did this so that this goes to this. So Now that we want to use this model and train it, that's a good question that we ask ourselves, actually, what did I do? And it seems like all I did, I tried to find the logic of where my irrelevant geo indications are, and it can change in different wells, can change in different applications. But that's all I'm doing. We are looking for unusual stuff in the scan. So here, for instance, we realized that in these well inspections, mostly these irrelevant are coming from cap geo. So for instance, here, you see an indication on this side. Seems like nominally you skip into the cap. There's a lot of them in the B scan. If it was a legit indication, you would expect that you would see it on the other skew, but you don't. This is a location of a cap. So you know what? This is probably irrelevant. So it seems like what I'm doing actually in my mind and brain that I might not realize because I'm doing this all day is I'm just paying attention to the position of this indication with respect to my weld and with respect to where my beam was. Same thing here for this other indication. Again, it's a second skip, is opposite side, it's close to the cap, and all the same reasoning. So ultimately, it seems like, again, what I'm doing, I'm paying attention to the position of this with respect to my overlay and make a decision. So it seems like position of these is a key feature that maybe we should give our machine learning algorithm to learn about, because it seems like that's what we do. So for that, we try to introduce these positional features. So we try to come up with the coordinate that we can put these indications on. But again, remember, we are dealing with the range of thicknesses, different levels. So we wanted to define a positional feature to be not sensitive to these changes as much as possible. And what we chose was a coordinate system that the edge of R has, and this index be x, how far the indication is from this corner, and the y be depth, like how far from the surface, but not just the absolute depth, because again, thicknesses can change. But we report divide by thickness as a ratio normalized to it be between 0 and 1. And now what we can do, it can actually plot these on the overlay. So here are two examples of irrelevant geo indications, and you can see that based on that coordinate, we see its depth and index and plot them on the overlay. And the same thing we do for the flaws that are actually relevant and are come here. And it seems like this is going to tell, it seems like if I do more of these, seems like it's going to build a region for me that unintentionally I'm thinking about that when I'm doing the analysis. That seems like there's a region that all the geo should be and a region that the defects should be. So let's do this more of this. So what we did, we took like 58 wells from one tower that had a range of thickness and bevels. We analyzed them in this analysis, which was fast, and we list all the irrelevant indications, and then we plot them with those positions on our beam tool overlay. And it starts to seem like these are clustering around two specific regions that we already see why. And there is some variations in them that seems weird a little bit at the beginning, because you see why there are like this much variation here, why there is variation there. First of all, in procedure, it isn't allowed for like 10 to 15 minutes of scanner drift. So in your scans, you can have that drift. Plus, this is just the shape that we put nominal. We don't know exactly how wide these welds are. So it might be larger, it might be smaller, different shapes. And also the other thing that was questioned, that why some of these, although if it's cap, why it show up underneath the, like under the surface or above the surface? The cap is after the surface. And that was explained by beam spread. And if, I don't know if you guys are aware of not, like last year at ASNT, actually we released a new version of beam tool 11, and we included a feature there which is point to spread function simulation, that it simulates, for any beam set, it simulates what kind of image you get from just a point reflector. And this is very useful here to explain. If you see where the mouse is as it moves on this, it shows you what would you get. It simulates what you would get as an image in your phase array system. It's unfocused one, so you get this, although at this place as my mouse is one tiny, tiny hole, but still it's like a large indication there. And if I go to vertical resolution map, it tells you that this can be huge indication. So even if your beam is here and there's no flaw here, part of your beam can interact with your cap and be plotted in the wrong spot, because you think the software thinks that it's plotting the data along this line. But guess what? Part of that beam spread is already catching your cap. So that means that the indication can be misplotted. So with this tool, now we understand this. Now we are not really as annoyed that why this is too variable. It all makes sense. But now we want our machine learning to come here and say, okay, we give you this data. We want you to figure out what is the boundary of this data. Because it doesn't seem to be a simple region to exclude. It seems to be complicated. So we want the category of the data we use is in the category of anomaly detection, that its goal is to define a boundary that contains as much of the data that you give it as a training data. So here, this model is specifically called one class support vector machine. And it used on a single class, because here we only use geos, not any defect. And it tried to learn what is the best boundary it can draw that include all this. Now that we have this boundary, these boundaries now can act as a flexible exclusion gate to say, okay, based on the data you gave me, seems like if you have a new data, if it show up in this boundary, it's probably geo. But if it show out outside of this boundary, it's defect. And at this point, I would be very happy to know if you tell yourself that, oh, this is simple, because that's great, that's the goal. I want it to be simple. That's what we're doing when I'm doing analysis, so I want the machine to do it. And I have no issue if it's simple. It's great. But how well it works? We go and we found another 20 welds from another tower scanned by different crew, so as different as it could be from our training set. And again, we analyzed them as analysis. Now, in those, we found 74 defects and 452 non-relevant defects. And from our training set, we didn't use our defects, and there were like 47 of them, so we included that also. So we ended up having 121 defects and 452 irrelevant indication. And we plot them now on that overlay. So the red points here are all the defects, and you notice that not even a single one goes into this region. So all of them are going to be classified correctly. All of the defects are going to be staying on the list correctly. And remember, all are already sized and categorized, all those things. But from these 452 indications, which has green points, there were only 8 of them that fall out, just barely outside of that. And before I comment on that, 8 out of 452 is 1.8% false call. And that's 1.8% chance that you, on your reports, you end up having an indication and you call it defect, which in fact it's not a defect, it's a geo. But to give it a better understanding of what that means, on average, these wells have 50 indications in them in general. And that 1.8% means that you can come up with up to 1 false call in your reports. In fact, when you look at these 20 wells that we had, there was 14 of these that had no misclassified indication on a report. It was just defects if there was a defect, but there was no misclassification. But there were 2 of those that had 2 false calls, like these guys, that the model called flaw, and 4 of them, only 1 false call. So I'm not going to comment on if this is good or bad. It's just what you can judge. But all I can say is that you have a 6-meter long scan. It's fully automated. And you may end up having 1 or 2 indications that are not actual flaw. But if there is actual relevant flaw, for sure you're going to detect it. So it can be good or bad, depending on how you think. But one important thing is that this is done with a fairly limited number of data. And as you keep doing that, you can keep refining your model and the boundary. And you see that the key point is that the points that are out are not way out. They're really close. So it means that you keep adding this data. You can refine this geometry, this boundary better and better and better. So the advantage of this, we believe, of these 2 steps, that you don't involve any model to do the critical task and just use the second step to refine this, is that it's very general and it generally needs not much data. The training data that you need for this is free to you. It's available to you. You are not making samples. You are not doing anything extra. The weld that you're scanning gives you that training data. So having the training data is guaranteed here, which is a big, big point. So now, if you want to implement this for a new inspection campaign, total new inspection campaign, wells we haven't seen before, how we think it's going to work. You first obviously design your techniques, procedures, scan plans, all that. But when we start the campaign, at the beginning, the human analysts need to use this analysis and analyze the first few wells. I don't have the exact number right now to tell you. Is it 20 wells is enough? Is 40 wells? I don't know at this point. But what I know is that with the time that you spend to do those with this software, already you're saving time and all those advantages of quality, even before automation. But as you're doing that in your first few welds, you are actually training or finding your training data, because you are actually, what your technicians are doing, they're actually labeling the data for you and saying what are relevant. And these data, the positions often can be unique. If there's a single V, the geo can show up differently. If there's double V, different welds, different caps, but it's typically unique for each inspection campaign. And when you get the positions of those in the first few welds that you analyze, you pass that to your machine learning algorithm, and it finds that boundary. That boundary gets saved in the software, and going forward, basically based on that, you have that boundary will be used to finalize the list. And again, you might get tired to hear this from me many times, but I want to emphasize one more time. None of the rules from any code, AWS, ISO, was like touched on. All of these things are done algorithmically, no AI involved in there, so there's no worry in that. And now what is now helping us to do is, as I said, now we are facing these many demands to automate things. Even there are some cases that in the productions, like in the factories, they are looking to do phased array now. And simply, it's hard to really do that without some sort of automation, because it's a very fast process. A component comes, you need to scan, mark, goes to repair, come back. It's just, and we have even clients right now in Acuren that we are doing work for them. We are doing this conventional duty, and now they want to switch to this. And now we have less challenge to answer that request by using this sort of automation. But it can go even beyond that. The new clients who come that they want to do in factory inspection, typically they haven't yet even chosen equipment to use. They haven't yet invested in any specific equipment. If they use equipment that can be controlled directly, like for instance, we are in this session, let's say Explorer from TPAC, it's even much easier and to use this as a dedicated for their system, because now you can have more advantages. We had done projects before with TPAC that with our Beam tool, we directly control their units because it's open source and they help us do that. So we make our scan plan, we basically send that scan plan to the device, you do the scan, and on the background, you don't even need to save data or anything. On the background, or export it to, on the background, the data goes back to our software, which at that point, maybe we need to call it automated analysis instead of SS analysis. It goes on the background, and you can move on to the next weld. You can go to the next weld, continue to scan. On the background, that data is going through this process, and report is being generated and being saved on the background. So this process can, and now you can think about, you can change the role of your personnel. If you had a crew before that, let's say 2 were doing data acquisition and 2 were doing analysis, now you can add those other 2 to help with the data inspection also, to speed up data inspection or help to get better quality data. And instead of analyzing one by one, maybe their roles change to audit the data. Every day they take one data on audit, make sure everything is good, but they don't need to spend that much time. And this system, we are really now excited to see how well it works. So I would also be happy to hear any comment you guys have, any data you have, you want to see this system, if you want to see a demo, if you want to have a trial, if you want to see how this works for your system and your data, I would be very interested if you can reach out. And at the very end, I hope that this information was useful to you. And at the very end, also, I want to thank Siemens Gamesa, because they let us make this data available to us so that we can do this work, and they share interest to consider that maybe implement this approach for their future inspections. Yeah, that's all I have. Thank you.